Okay, so I want to thank Tobias for his presentation, and of course, the organizer of the conference. So I'm Mark Avesani. I'm going to tell you about a recent work we have done at the University of Padova with Davide Marangon, Professor Giuseppe Vallone, and Professor Paolo Villoresi. So we propose a new source device-independent protocol for quantum random number generation that employs generic discrete variable or continuous variable POVMs, and we experimentally implemented it using heterodyne detection, reaching more than 17 gigabit per second of secure generation rate. So as Tobias was saying, when we have QRNGs, there is a sort of trade-off. So we either go for trusted QRNG that delivers the highest performances, but they are trusted in every single element of their devices, so they offer the least level of security. On the other hand, device-independent protocols offer the highest level of security, but they are extremely complex to realize, and also they are slow. So another option is given by semi-device independent protocols. These are a sort of compromise between the two, and they are usually prepare and measure protocols that work in the same paranoid scenario as device independent, but they do assume something about the inner working of the devices. This can either be the underlying dimension of the Hilbert space, something about the source, or something about the measurement station. So they're a compromise because they can deliver a security level much higher than trusted QRNGs, but at the same time, they offer performances that are dramatically higher than device independent. So in our work, we wanted to boost the performance of these semi-device independent protocols to be on par the one of trusted QRNGs, while keeping the experimental complexity low. So this is the skeleton of our protocol. It's source device independent, so we don't make any assumption on the devices, and that is fully controlled by Eve. So at each round of the protocol, Eve can freely choose to send a state that she forges to Alice. We can also see this with Eve and Alice sharing a generic quantum bipartite state that is fully controlled by Eve. So at each round of the protocol, Alice will get a random state, an unknown state, and she will measure with one of her POVM. These don't need to be ideal, but need to be trusted in the sense that we must know their shape. So Alice will get some outcomes, and these form her raw numbers. In general, these are still could be correlated with Eve, since Eve holds some quantum side information. So what we need to do is to estimate the quantum conditional mean entropy that will basically tell us how many private bit Alice holds, given that Eve has some quantum side information. And then we use the leftover hashing lemma to extract from the raw numbers, the secure numbers, that are no longer correlated with Eve. So we can write the quantum conditional mean entropy in terms of the p-guess, which is basically Eve's probability of correctly guessing Alice's output. So Eve has the ability to forge the state that she wants, and in general, she can decompose it. She can forge the state as an incoherent superposition of these states, tau beta, that can also be non-orthogonal, with some probability distribution. And so our best strategy is to find those states and those probability that maximize one of the outcome of Alice's POVM. So if Alice is using a projective measurement, is easy, because she can always find a state that has a maximum overlap, so that we'll get an outcome with probability 1. But this is no longer true for, the story is different for over-complete POVMs. In fact, consider the heterodyne POVM. This is just a projection onto the coherent states, and is overcomplete because the coherent states are non-orthogonal. So Eve knows that Alice is going to measure with this POVM, and she prepares her best possible state that, let's say, is this one. But Alice could measure with this state, on this state, or even this state. So just having an overlap on the POVMs makes sure that even if Eve knows what will be the measurement, she cannot force one of the output with probability 1. So if we just insert the heterodyne POVM structure in the PGAS formula, we can see that it is always bounded by the maximum of the Usimi-Q function. But the Usimi-Q function is always bounded between 0 and 1 over pi for any possible physical state. So that means that Eve, even if she knows that L is going to measure with the heterodyne POVM, cannot guess L's outcome with a probability higher than 1 over pi. However, in the lab, we only have access to practical devices that can sample the phase space with a finite resolution. So, and this leads to a discretization in the phase space. So if we take into account this, we gain another two factors, these delta P and delta Q, that are basically our resolution in, our measurement resolution in the phase space. And with this, we can bound the PGAS and so the mean entropy. So I want to highlight some key difference between our protocol and other typical semi-device independent protocols. So the first one is that we don't need input randomness. Usually in semi-device independent protocols, but also in device independent, Alice and Bob are playing some quantum games and they are selecting some settings on their boxes, and they need an external source of randomness for that. While in our protocol, we don't need that. Another difference is given by the fact that, again, in semi-device independent and typical semi-device independent and device independent, the user plays this game and look at the output probabilities, the experimental probabilities, and then they can bound the mean entropy. Here, instead, just having the structure of our POVM and the resolution of our experimental apparatus, we can already bound a priori the quantum conditional mean entropy. Moreover, we work with the single-shot entropy measures, and also we have non-estimation involved. So we already are working in the non-asymptotic case. So we go down in the lab and implement this. So the source is untrusted, so we can use the simplest one that we can think of, that is just a vacuum. So we insert the vacuum in one of the heterodyne ports. The heterodyne detection that samples both quadratures is made using a 19-degree optical hybrid that uses a strong laser as a local oscillator. It's a 1550 nanometer laser that is monitoring in real time. Here we have a 90-10 beam splitter in which we can monitor in real time the local oscillator. With that, if we have fluctuation, we can compensate in the post-processing without affecting security. Then we use two balanced detectors with 1.6 gigahertz of bandwidth, and we sample the signals with an oscilloscope that has 10 bits of resolution, 4 gigahertz, and we sample it at 10 gigasamples per second in burst mode, so no real time. I want to stress that the electronic noise here is not trusted. So it is considered as a noise on the source, and so it will decrease our performances, but will not affect the security. So finally, we use a Toeplitz randomness extractor to get the secure numbers, having the mean entropy that we estimated. So the results, so our apparatus has 10 bits of resolution, and we get this equivalent resolution in the phase space. With the heterodyne detection, we gain for free tomography in the phase space, and this is the difference between our real data and what we expect for the vacuum. This slightly bigger distribution is due to the fact that we don't trust the electronic noise. So with this resolution, we get more than 13.9 bits of mean entropy per sample, and we have an effective sampling rate of 1.25 gigasample per second. So we reach this more than 17.4 gigabit per second of secure generation rate. So to conclude, we have proposed a new source device independent protocol valid for any discrete and continuous variable POVM. The protocol doesn't require external randomness and doesn't depend on the measured data, the security at least, and is already valid in the non-asymptotic case. Moreover, the experimental setup is simple and only use commercial off-the-shelf components, and the performance are almost on par with the best trusted QNGs. we want to improve having real-time filtering and extraction on hardware, and also try to weaken the assumption on the measurements. So, thank you for the attention.
Thank you very much. Questions for the two speakers? I have a quick question. You mentioned the final bit rate is 17 gigabit per second. Mm-hmm. Is that the real-time extraction?
No, it's not real-time.
Okay.
No.
Okay. And what is the size of the top list matrix?
So we can more or less choose the size of the top list matrix depending if we want to save memory on the computer or have performance. I think if for this extraction we used 4096, then multiplied for the equivalent mean entropy ratio.
And also, I have a quick question for Tobias. Regarding the homodyne detector, do you measure the bandwidth of the detector and also the common mode rejection ratio between the quantum noise and the classical electronics noise?
Yes, we characterize that with what I explained, basically using a second laser source, beating it so that we get a beat frequency, then tuning this laser. And this gives rise then to our model for our vacuum fluctuations. If you have, so this is this part, it's actually a very fundamental part in it, because this gives us the power spectral density of the vacuum fluctuations, and it's not flat, right? And that means basically that we have correlations in the system that have to be included. For the common mode rejection, so if you assume that you have, if you don't have a very good common mode rejection, then for example, the relative intensity noise of the laser convolutes your measurement. And this is basically part of the excess noise part, because we know what exactly is the part of the vacuum fluctuations. And by measuring everything and subtracting what we trust to be the vacuum fluctuations, that's what I called excess noise. And excess noise is the electronic noise of the detector and relative intensity noise that gets into the system because of bad common mode rejection.
Okay, thank you. Any other question?
One more question. At the last slide, the outlook, you mentioned the potential for the QKD chip. You want to total integration. Mm-hmm. Can you give us more detail? How do you integrate? What means the total integration? You slide. Yes. The last page.
Yes. So if you want to integrate a random number generator into a QKD system, our first question is it a CV QKD system doing Gaussian modulation, or is it a discrete variable system? But in the end, what you get is, so we have the random numbers extracted on an FPGA. And then you would either transfer them to a computer and use them maybe with some other hardware to actually drive the modulators. Or for CVQKD, I would rather suggest to actually do everything on the same FPGA. Because what you need to do is you get an amount of 10.67 gigabit per second. That's quite a large data rate. And then you need to generate Gaussian random numbers. And you can actually do that on the FPGA as well. And then you maybe use 8-bit for one sample in a CVQKD system so that you actually can reduce the rate already. So then you can connect your FPGA to a digital to analog converter and directly drive the IQ modulators in a CVQKD system. So I think this is how I would do it. I would actually take the FPGA as part of the QKD system. I think this is most practical.
Any other question? If no question, this session is finished. Please thank all speakers in session again.